part. Let's talk about that. Okay, so on this warm-up, right, we're finding the derivative of the inverse cosine of 4x, or in other words, the arc cosine. And we got down here to this is our answer. And Brandon is asking, how did you get the second part? Are you saying this part right here? This part that I'm circling? Yes? Okay, so remember, if you have a composite function and you're looking for its derivative, meaning if you have a function inside a function, right, and I'm looking to take the derivative of this, we use the chain rule, right? And the chain rule simply states that you need to multiply the derivative of the inside function times the derivative of the outside function evaluated at the inside function. So that 4 right there represents the derivative of the inside function. So, well, the second parentheses. Okay, yeah, okay. So yeah. So the derivative of your inverse cosine is a bunch of those rules that I had you memorize, right? I was trying to tell you to memorize. Give me 1 second. Let me go get a marker real quick here. Oh, I lied. I can't find a marker. Oh, wait, here we go. Yeah. So I promised I was going to keep them on the board behind me. And let's see if I can do that real quick here. So one of the derivatives, right, was going to be for the inverse of sine x, right? And if you take the derivative of that with respect to x, right, you'll get 1 over the square root of 1 minus x squared. The second parentheses, Brandon, then is coming from the derivative of the inverse of cosine. So d dx with the inverse of cosine of x, and that's going to be equal to -1 over the square root of 1 minus x squared. That's where that second parentheses is coming from, except it's not the inverse cosine of x, right? That's where that is. It would be that x right there, but since it has a 4x inside there, that's what it's going to be instead, that 4x right here. Does that make sense or no? I don't know if that makes sense. This whole thing in the second parentheses is the derivative of the inverse of cosine. Yeah, and there were 6 of them in total that I told you guys to try to know or try to memorize. Let me see here if I can get those 6 here on screen somewhere. Where are you? Is it here? There we go. There we go. So those are the 6 that you need to get down and you need to know, right? The derivative of the inverse of sine, derivative of inverse of cosine, and all of their friends. Tangent, secant, cosecant, and cotangent. Which, yeah, does that answer your question, Brandon? I'm not sure. Let me know. That's where that comes from. It's this guy right here that we were using. Okay? Yeah, awesome. Okay, so let's go back. And there we go. So that's it. That's the answer for that one. Let's go ahead and take a look at number 2. Like I was saying, there's a couple ways you can do this, but it looks like the majority of you guys who are doing it on the pair deck, we're doing this implicitly, right? Implicit just means that it's not solved for the y variable by itself. Does that make sense? Since it has a combination of x and y put together, we have to do this implicitly. Explicitly is if it was like y equal, that's a highlighter, not me. If you had, for example, y equals like your thing, and no y's are involved on the other side, it's just a function of x over there, you could just have it explicitly done. And that's what we did for the first half of this chapter, right? So taking a look at this one right here, we're going to go ahead and take the derivative of this left side implicitly, which means that this is going to be on the inside, x cubed plus y, and on the outside, we have sine of some stuff, right? So you're going to chain rule this for yourself, okay? And the way we're going to do that, right, is take the derivative of the inside. Derivative of the inside is going to be 3x squared plus the derivative of y, which is just 1. But then again, you also have to remember you're taking the derivative of y with respect to x. So that's going to be 1 dy dx, right? That's the derivative of the inside, right? Multiply that with the derivative of the outside. Derivative of sine is just going to be cosine of the stuff that you have written inside there, which is x cubed plus y. See that? And this, of course, is going to be equal to, what's the derivative of x? Derivative of x is just going to be equal to 1. Now this is where you got to be careful. Remember what you're solving for. You got to make sure your algebra skills are up to par for this right here. We're trying to get this dy dx by itself. And I know a lot of you guys would probably try to subtract the 3x first, but that's not what you can do because I can't subtract it because it's in parentheses and it has to deal with this multiplication of cosine of some stuff first. So this one actually goes a little bit backwards. You actually should be dividing by that cosine first. I know that sounds wonky, but it's because this cosine doesn't have a dy dx in there. I don't need this term at all, and it's not adding with the problem. It's actually multiplying with it. So you got to use your skills here and divide that cosine over to the other side before you do anything else. So I'm going to go ahead and divide this cosine of x cubed plus y over to the other side. So then now, right, all that's left on the left-hand side is 3x squared plus dy dx is equal to 1 over cosine of x cubed plus y. I know this one's a little bit more backwards than the other problems that we've been doing, but it's just how it is. It's multiplying here, and I can't get rid of this 3x squared that's inside this parentheses until I get rid of the parentheses itself, which is multiplying with something else. So I divide by that something else. Now I can get rid of this 3x squared by subtracting from both sides. And when I do that, I end up with my nice dy dx by itself. And this is where the part that's kind of weird here, but this is it. This would be your answer. 1 over cosine of x cubed plus y minus 3x squared. And that's it. That's your answer. I know that sounds kind of strange, but that's just, like I said, that's an algebra thing that you guys got to be okay with, right? It's the fact that that cosine of x cubed plus y needs to be gotten rid of first before we can get rid of that 3x squared. Is that okay? Does that make sense, guys? If not, can you guys let me know? Because I know that some students actually have this urge to distribute the cosine into both things, and that wouldn't be wrong. You could do that. It just gives you more work to do when you go in there and try to simplify and solve for the dy dx. Okay? All right. Side note, don't write this part down unless you really want to. You could solve for y algebraically before you even do anything, before you even take the derivative. Side note. So let's take a look here. So I'm saying that for sine of x cubed plus y is equal to x, you could solve for y. Because I told you, these equations, you can get rid of like trig functions by doing their inverses, right? So I'm saying that if you do the inverse of sine of x cubed plus y, if you do that to both sides, this actually cancels out. Sine and inverse of sine, a function and its inverse actually cancel each other out, and you're left with just what's on the inside of that said function. I know that sounds weird, but that's the idea, right? That's the whole reason why natural logs and e exist, by the way. Natural log and e are inverses of each other. Sine and inverse sine are basically inverses of each other as well, and they would cancel each other out, and you'd actually be left with this. X cubed plus y is equal to the inverse sine of x. And then you could just move the x cubed over to the other side, and you'll end up with y is equal to the inverse sine of x minus 3x cubed. I don't know if you guys are seeing what I'm doing here. And then from here, this now is no longer implicit differentiation. This is now explicit, right? It's now explicit. It's y equals to only the terms of x. What do you do when it says in terms of x and y? It doesn't. That just means that it can be either one of them. That's all it is. It's just like in terms of x's and y's, it doesn't have anything else in there. If it doesn't have any y's, then that's perfectly fine as well, as long as you've done it correctly. Does that make sense? Yeah, that's all that's saying. Like, oh, in terms of y, meaning that your answer was only in x's and y's. And if there's no y's, that's in this case right here, that's okay. So right here, if I take the derivative here with respect to x, I'll get dy dx on the left side, right? And then on the right side, the derivative of inverse of is technically 1 over the square root of 1 minus x squared. Minus the derivative of x cubed is going to be 3x squared. And this is the part I always found kind of interesting and kind of weird. And you look at it and you're like, knock me, what the heck? that doesn't look like what we got when we did it implicitly, but actually they are the same. I know that sounds weird, but they are the same. If you actually take a number and plug it in for x and y into both of them, it does work out. And it is something I suggest that you guys take a look at and try on your own time. It's just kind of neat, but it's not necessary. But it's just kind of neat to see that, you know, that's one of the more difficult things about calculus. It's just the fact that you have multiple ways of doing problems now. And which way is the correct way isn't actually a solid statement anymore. You might be able to find out one way might be easier than another, but you might not know until you try it. And that's going to be the case for a lot of these calculus problems. And it's a frustrating thing for if this is the first time you're ever thinking if you're trying to solve a problem differently than just like, oh, I just follow these steps. There's going to be so many problems where they're not going to tell you which steps you should go with. You kind of just have to see which one works. And if it doesn't, you try something else. And then it's like, well, how do I know to try something else? You don't. You just try it. And if it doesn't work, you try something else. And you try something else again. I know that's like, that sounds frustrating. And I say it sounds kind of fun, you know? Math isn't supposed to be this boring thing where you just do the same steps over and over again. Math is supposed to be this tool that helps you problem solve. So if you come across something that you can't solve, you find another way to solve that problem. Anyways, I'm getting too sidetracked again like I normally do. So let's go ahead. That's it for 3.3, by the way. Know these inverse trig functions: sine, cosine, tangent, cotangent, cosecant, and secant. Know their derivatives for the regular trig functions, and know the derivatives for their inverses as well. You need to get those down by heart. So I'm going to give you some time. You either make some flashcards, get them down memorized. There will be quizzes on them, trying to see if you guys know which one is the derivative for which. Okay, and we're going to go ahead and start up on our last section for this chapter. You're like, what? Last section already? I feel like we just started. And yeah, chapter 2 and chapter 3, when I first taught this class, I taught them together as one big chunk with the chain rule, product rule, quotient rule, and these derivative rules of trig functions. And it was just a lot. So the past couple years, it's been split up into 2 sections, 2 smaller sections. So the first section, chapter 2, was a little bit smaller, and chapter 3 is a little bit smaller, but I'm thinking it's a little bit easier to deal with when you deal with them into these smaller chunks and their derivatives, right? Anyways, my back is feeling kind of weird. Anyways, so let's go ahead and jump into this last topic right here, which are some advanced derivatives, right? Some advanced derivatives. So the first one up, right, is what we just started talking about, which were inverse trig functions, which then leads us to our next topic. Then how do you find derivatives of just inverse functions in general, right? So let's go ahead and write that down. So we're going to be looking at, this is the first part of this topic for advanced derivatives. This is basically, how do you find the derivatives functions? I can't write today. Inverse functions. The tangent line, right? So if you have a function and you find its derivative, you found its slope, pretty much. And what I'm saying is, if I have an inverse function, what is the derivative of that said inverse function? Okay. So are you guys familiar, by the way, with what an inverse function is already? Like we talked about it for the trig function, but maybe we can talk about one that's a little bit easier to deal with. Okay. So let's take a look here. Can you guys imagine with me a function? And I'm going to say that this function is going to be equal to, I don't know. Let's say it's equal to 2x minus 1, let's say. 2x minus 1. You guys okay? That's a simple linear function, right? And if you understand what a function does, right, it takes your numbers that are in the domain. So for example, like 0, 1, and 2, right? It takes your numbers that are in the domain, and what the function f of x does is it transfers it to the numbers that are in the range, right? So for example, 0 would be mapped to -1, 1 would be mapped to 1, and 2 would be mapped to 3, right? If you plugged in the numbers in for that x value right there into the function, right? So that's all a function does. It takes it and it maps it over there, okay? An inverse function, let's let g of x be equal to the inverse function of f of x, right? Everything from the range and spits it back to the domain. Do you guys remember how to find an inverse function? Do you guys remember how to find an inverse function? If f of x is equal to, let's say f of x is equal to 2x minus 1, do you guys remember how you're supposed to tell me what g of x is equal to? Do you guys remember that? Do you guys ever work on finding inverse functions? I'm gonna pause it for a second. Anyone? Anybody? Anyone have an idea of what the inverse function should be for 2x minus 1? No. Thank you for being honest with me, Max. You probably do if I actually started working it out and you saw it, but it's been a while, I'm pretty sure. Inverse functions aren't actually talked about too often, but it is a neat little thing. All right, let me explain this for you then. So here's the thing. You don't have to write this part down, but I can't go on without actually explaining this to you. So if the function f of x, right, is equal to 2x minus 1, okay? To find the inverse function, to find g of x, which is f inverse of x, right? What you need to do is replace the f of x with the y and write this as y is equal to 2x minus 1, and then you switch the variables around because the inverse switches your input and your output, your domain and your range. So you would rewrite this as x equals to 2y minus 1 to help you to find this inverse. And then you would solve for y. So you'd add the 1 over, you get x plus 1 is equal to 2y, and then divide both sides by 2. And what that leads you to is your y equaling to x plus 1 over 2, which is not actually y, that's actually your inverse function. And that, right? So that x plus 1 divided by 2, or if you simplify that out, that's going to be x over 2 plus 1/2. That would be your inverse function. Does that make sense? Does that kind of like, does that look familiar at all? Have you ever done something like this before where you switch the x's and the y's and you solve for it? That's how you find inverse functions, by the way. Okay. Now, if you look at this inverse function of x divided by 2 plus 1/2, right? What I'm saying, plug in a number in for the range. For example, if I plugged in 3, right, into my inverse function, I will get 3 divided by 2, which is 1.5, plus 1/2. 1.5 plus 0.5 would give me this 2. And that's going to work for all of these numbers. If I plug in 1, I'll get 1 divided by 2, which is 1/2, right? And 1/2 plus 1/2 is going to give me 1. So that's how the inverse function works. It takes all the numbers that you have in your range and it just spits it back out. And it's just another function. It's just another function. Okay? Now, here's the thing, though. What we're talking about for this to be this isn't calculus, by the way. This is all Algebra 1 stuff. This is stuff that you should have learned in your IM1 class or at least your IM2 class or 3. I forget. It's one of the earlier classes on how to find these inverses. What makes this the calculus part is we're going to connect their derivatives together. Okay? So if you take a look here, the derivative of f of x in this particular example is equal to 2. Okay? Well, if you look at the g function, its derivative is equal to x over 2 is the same thing as 1/2 of x. So derivative of 1/2 of x is just going to be 1 over 2. And there's a connection here and here that I want you to. The number there is the same, and it's not by coincidence. It's actually the same because of the way that their slopes work when you look at an inverse and its original function, right? Think about this. What a function does is it takes numbers like, for example, 0, and it spits out -1, right? What the inverse function does is it's going to take 1 and spit back out 0. I'm sorry, -1. So it switches your x's and your y's around, right? And when you switch your x and your y around, it reflects it across this graph of y equals x. And let me show you what I mean. I'm going to go ahead and type this up, and then I'll show it to you on my favorite graphing app, Desmos. It's a free app, right? Even though you have a free TI calculator, I should be using that more. We should be practicing that because on the AP exam, you will need to use that, but we'll do that later. So let's say I have here y is equal to 2x. Was it plus 1 or minus 1? It was 2x minus 1, right? So it's a graph that looks something like this. Okay. And then its inverse, right? Its inverse was y was equal to x over 2 plus 1 over 2. Right? And what I'm saying here is, if you look at that graph, right, they're reflecting across each other. I don't know if you can tell this or not, but they are reflecting across this particular line. Whoa. There you go. It's reflecting across this particular line, y is equal to x. And again, I don't know if this is all ringing a bell or not, but I'm hoping it does, right? An inverse function mirrors itself. So for example here, if I take a look at this point right here, this point is 0, 1. When you reflect it over that line, it maps over to -1, 0. Okay? And it does that for a lot of them. For example, right here, this point on the original function was at, let's say, 2, 3. On the inverse of it, it flips over to 3, 2. I can't. There you go, 3, 2. So what an inverse function does is just switches it back and forth, right? So how does that lead to this whole thing here? There's a connection here with this derivative and that one right here. So let me just give it to you right now, okay? So here's the deal. Let f of x, right, be differentiable. Let f of x be differentiable and g of x equal to the inverse of f of x, right, like we did earlier. If you're looking for the derivative of its inverse, then the derivative of the inverse function is simply just equal to 1 divided by the derivative of the f function evaluated at g of x. And this is basically a shortcut is what I'm trying to show you guys. So earlier when I had these functions right here and I was looking for the derivative of g of x, all I really needed to do was I didn't even need to find out. You're like, what does this all mean? Let me just do a problem for you and then work this out for you. What I'm saying is sometimes if you're looking for the derivative of the inverse function, you don't need to find the inverse function. And in fact, knowing that makes it a lot easier because sometimes finding the inverse function is not that easy. This one was an easy inverse to find because you could just solve this linear problem. If you're dealing with something that's cubic or sometimes even quadratics, finding the inverse function is quite difficult. And then once you for it, but when I'm telling you the stuff that you learned back in algebra, finding the inverse is not as easy, right? Finding the inverse is not as easy. So anyways, let's keep this in mind. Let's do an example problem. And I think I spent too much time rambling here. If you actually see a problem, you're going to realize like, wow, that's it. And yes, that's pretty much it. So let's take a look here at a problem where I have f of x is equal to x cubed plus 3x plus 10, right? Okay, and I'm going to let g of x be equal to the inverse of f of x. Okay? They want me, and then also, you know what, just to throw it in there just to make it a little bit easier here, like, look at this function, and would you agree that finding the inverse function for this is actually going to be a little difficult? Remember earlier I showed you guys, what you need to do is actually switch the x's and the y's with each other. So if I switched it as x is equal to y cubed plus 3y plus 10, would you guys agree to find the inverse itself? This would be annoying. You have to solve for y, and I don't know how to solve that cubic, right? Do you guys know how to solve this cubic? Do you know how to get y by its the quadratic formula? Well, we were never really taught the cubic formula, which by the way does exist, and it's just horribly lengthy, so we don't bother with it. So finding the inverse is too much work if all I'm being asked for is to find the derivative of the inverse function. If I was asked to find the derivative of the inverse function, I wouldn't have to do all of that. And the derivative of the inverse function evaluated at 24. Okay. So in order for this to work, by the way, I need to know what the inverse function would spit out if I plugged in 24. In other words, I need to know what function value evaluated at is going to give me 24. And I'm just like spewing up like, what the heck are you saying with all these numbers? So I'm saying this here. Let's just keep it simple right here. And I just want to show you guys real quick. I'm going to give you this one right here. So f of 2, right? If you plugged in 2 here, 2 cubed is going to give me 8 plus 3 times 2, which is going to give me 6. 8 plus 6 is 14. 14 plus 10 is going to give me this 24. Most of the times, a lot of these problems are going to give you something like this. They're going to give you like, oh, f of 2 is equal to 24, or they'll write it as, you know that one point is on this function, f of x, is 2 comma 24. These are the same thing. These two things are saying the same thing. Okay? All right. So let's do this problem. How do I find the derivative of g evaluated at 24? Use the shortcut I gave you guys right here. So derivative of g evaluated at 24 is going to be equal to 1 over the derivative of f evaluated at g of 24. So if you're looking for the derivative of the inverse function, you really only need two things. You need the derivative of the original function, and you need the inverse function evaluated at the point that you're interested in. So if the point is 24, I need to find the inverse value of 24, and I need to find the derivative of f of x. So here's the deal. If you know that f of 2 is equal to 24, and you know that g of x is the inverse of that function, that means that g of 24 would just go backwards, and g of 24 is going to equal to 2. So that's the first thing you need to find out, and that's actually the first thing that gets plugged into here. G of 24 is technically just equal to 2. Okay? So if I'm looking for the derivative of the g function, derivative of the inverse function, evaluated at 24, this is going to equal to 1 over the derivative of the original f function evaluated at 2. So I need to just plug in 2 into the derivative of the original function. Well, how do I find the original function's derivative? It's what we've been doing for this entire chapter, right? The derivative of f of x is simply just equal to 3x squared plus 3. Are you guys following along? Right? So if I'm looking just for the derivative of f of x evaluated at 2, I just plug in 2 into the derivative. Where is that 2 coming from? That 2 is coming from the g of 24. How did I know the g of 24 is equal to 2? I know that f of 2 is equal to 24, so they are inverses. They go back and forth with each other. All right? So simplify this out and evaluate f prime of 2. That's going to be equal to 2 squared, which is 4. 4 times 3 is 12. 12 plus 3 is 15. So my answer for this problem, the derivative of the inverse function evaluated at 24, is simply going to be equal to 1 over 15. And that's it. And that's it. So, yeah. I don't know if that made sense or if that just like was like, what the heck is that? It's really just you're supposed to just take this as a shortcut. I went on this whole long-winded rant about it just because I hate just giving shortcuts without an explanation of where they come from. Okay, and I haven't actually explained where the shortcut comes from, but I'm just basically showing you what's going on with these pieces in there of the shortcut on how this works. Okay, so let me give you a second to copy that down. While you're copying that down, though, I want to show you something that relates this. So give me 1 second while you guys are copying that down. Let me go ahead and write this up. I don't know if this is going to work. F of x is equal to x cubed plus 3x 10. All right. G of x is equal to f of -1 this work? That doesn't work. Maybe if I do it this way. No, that doesn't work. That just makes it the reciprocal. Yeah, I can't actually show it to you on Desmos, or at least I don't have it ready for it. But yeah, sadly. Okay, so anyways, for right now, right, we're going to be using this guy to help us to calculate our derivatives of inverse functions, just simply because, I don't know about you, but sometimes you won't be able to find the inverse of a function. And it's been a while since you've actually practiced finding the inverse of a function. And I'm just letting you know, you don't need to find the inverse of it. You can just use the original function itself and then know what values is the inverse taking it back to. If you can know that, you'll be able to do these problems, right? So let's go ahead and do another problem. Practice this out, and then I'll explain a little bit more where this guy is coming from. So let's do another problem. So let's do another example here. Okay. So let's say I have, for example, let f of x be equal to 2x cubed plus 2x squared plus x, right? And the point -2 comma -10 is on the graph of f. Okay. Let's see here. If g of x is the inverse function of f, what is the value of g prime of -10? All right. So again, g is the inverse function, right? And the function that we're dealing with is 2x cubed plus 2x squared plus x. And that's just something that I don't want to deal with finding the inverse of. And then honestly, in all honesty, I don't know how to find the inverse of that. It is possible to do, but honestly, it's past my skill level. I would not be able to do that. I do not know the cubic equation that would help us to solve that. So instead, if I'm just looking to find the derivative, I do know the calculus part of this, though. I can trust in my calculus skills to find the derivative of the inverse function evaluated at -10. That is something I can do. You ready? Here we go. So let's say I was asked to do this. Well, I know that the derivative of the inverse function is equal to 1 divided by the derivative of the original function evaluated at the inverse function of that point that I care about. So the point that is in question right now is at -10. So I'm going to be looking for the derivative of f of x, but not f of x, but f of whatever g of -10 is. So I need to find two things in order for this to work, right? In order for me to find g prime of -10, I need to find, first of all, what the heck is g of 10, right? What the heck is g of 10? And once I find that, I'm going to plug it inside the derivative of f of x, okay? I'm going to find the derivative of this right here. So first things first, what is g of 10 equal to? Anyone have a guess? Anyone have any wild suspicions of what you think g of, I'm sorry, that should be a -10, Naki? Not a 10, that should be a -10. Thank you. There we go. That would have been a bad mistake, but yeah. And a lot of people already started typing. Yeah. Thank you, Brian. I think you were about to catch that. That's awesome. And then everybody else typed in the answer already. You got the right gut feeling. G of -10 is going to be -2. The reason is f of -2 is -10. G is the inverse. It takes it and it goes backwards with it. They flip it around. They flip it around. So g of negative 10 is negative 2, right? The second thing then, so I already have this part done. I have this part right here. This negative 2 is going to go in for this g of negative 10. That part's beautiful. That means then I'm looking for the derivative evaluated at negative 2. So let's go ahead and find the derivative of f of x. Well, I go into this function, and I love this. The calculus is easy. I take the derivative of this guy. That's the easiest derivative we've done in a while, isn't it? 2x cubed is going to be 6x squared plus 2x squared is going to become 4x, and the derivative of x itself is just going to become a 1, right? Which means then all I have to do now is evaluate the derivative at negative 2. So I'm going to plug that in. So it'll be 6 times negative 2 squared plus 4 times negative 2 plus 1, which is going to give me, I believe that is going to be 4 times 6 is 24 minus 8. So 24 minus 8 is that 16, right? 16 plus 1, this is going to be a 17. So I know that this right here, f of g of negative 10, f prime of g of negative 10, right? Because that negative 10 is actually that g of negative 10 is actually that 2, is going to be equal to 17. So the derivative of my inverse function evaluated at negative 10 is equal to 1 over 17. And that's it. That's your answer. And I know I went on this whole long-winded thing when I like, knock me. That's it. You could have just showed me that. Again, I have like this issue of showing you things without explaining to you, like there's a connection between this, and there are things that are working along the ways. And I still haven't even shown you the connection there. I just want to make sure you guys are okay with finding inverse values, right? Or does that make sense? How did those 3-4 people know that g of negative 10 was going to equal to negative 2? Are you guys okay with that? And what if I didn't give you this point? What if I didn't give you that f of negative 2 is equal to negative 10? Would you be able to find out what it was? And there's a couple tricks for you to do that. Okay? I'm going to show you one trick right now. So let's say they didn't tell you that f of negative 2 is equal to negative 10, but they did want you to find g prime of negative 10. Would we plug in negative 10? You're close, Monica. You're close. You would actually set this equation equal to negative 10 and solve for when does x equal to that. That's one way you could do it. The only problem is there might be multiple points where it's equal to negative 10, right? So also solving that, like I said, solving that cubic, if it's not a factorable one, it's very ugly to try to solve. So usually when that is the case, Monica, if they don't give you a point, they'll give you this problem in a calculator section. And the reason why it's going to be in the calculator section is you would graph this and see where does it equal to negative 10, and then you would go backwards on that. So let me show you what I mean. So let me open up my graphing calculator here. You guys have a fancier one with color, so it's going to be looking a little bit better. But let me go ahead and show you this guy right here. This is going to be here 2x cubed, right? 2x cubed plus 2x squared plus x, right? Plus x. And if you go ahead and graph that, it looks something like this, right? But I'm looking to see when does this thing equal to negative 10. So I'm looking, and I'll draw another line right here. I'm looking to see when does that graph equal to negative 10. So I set up a second equation. When would this thing equal to negative 10? Let's say, right, I didn't know that was negative 2. I just wanted to see it because they told us this part. Well, I would graph this, right? And I see that, oh, it's crossing right down here. On your calculator function, you can actually, unlike Desmos, you can just click on it and see where they cross. This one, you can actually do this right here. You hit second and trace, and it will calculate where your two graphs intersect. So I'm going to go ahead and go down to the 5th option right there. And I'm looking to see where they intersect. So the first curve, I'm going to go down here. I'm looking to see where does it cross at right there. On the second curve, it's about there. And I go ahead and press enter on my guess. And it tells you me right there. Where does it intersect? It intersects at negative 2, negative 10. Bam. That's what I have as my answer right here for negative 2, negative 10. So then therefore, the inverse function would take negative 10 and spit out negative 2. You guys see that? That's how an inverse function works. It takes out what was your output originally and takes you back to what was your input, right? What is it? It works it backwards is what I'm trying to say, right? So that's the case on how that works. Okay? Again, if you're lost on this whole thing of everything I'm saying here, then basically just memorize this. you're going to get a problem, and I've seen it for the past couple of years. There's always been at least one problem on this on the AP exam where they ask you to find the derivative of the inverse of a function. And instead of wasting like 10 minutes trying to find out what the inverse is and then taking the derivative, you could just use this shortcut. You can just use this shortcut. Now you'll say, God, that's another formula that I have to memorize. You already have me memorizing these inverse trig functions over here, and that's already a lot. And then I have to memorize the product rule, the chain rule, the quotient rule. And I agree with you. That is a lot of things that you have to memorize. And I'm not saying that you should memorize them. There actually is a way that you can derive this. And I'm going to show you this real quick. All right? If you already understand how to do this and you don't want to do this part, you can just tune me out for this one. But I just wanted to show you, you can derive this shortcut. And it's actually a fairly easy way to derive it. Okay, so check this out. If g of x is equal to the inverse of f of x, right? And f of x is a differentiable function, right? So we have this right here. Hear me out. If I have the inverse function and then take it with the original function, what you should understand is that the inverse function and the original function would cancel each other out, right? And you're just left with x. So if you ever have a function and its inverse function of each other, just like if you had sine of inverse of sine of x, that would just equal to x, because the sine and the inverse sine would just cancel each other out, like our warm-up we did today. Now, why is that important? We've learned the chain rule, right? And we can apply the chain rule. And this is what my favorite thing about calculus is. If you learn some of these rules, you can apply them to different levels, and you don't have to memorize more things. You could just see that they work each time you go. So check this out. On the right-hand side, the derivative of x is just 1, right? The derivative of x is just 1. The left-hand side, the derivative of f of g of x is the chain rule. The inside function is g of x, and what's the derivative of the inside function? We're just going to call that g prime of x for now. Multiplied with the derivative of the outside function. Well, what's the outside function? The outside function is f of some stuff. Well, what's the derivative of f? It's just f prime of some stuff. But what's that stuff that's in there? That stuff that's in there is g of x. Remember, our ultimate goal was to find out what is the derivative of the inverse function. So I can take this and then divide by this f prime of some stuff. Divide it to both sides. And when I do that, this cancels out over here, and I'm left with just g prime of x. And this is equal to, lo and behold, the shortcut that I've been trying to teach you, f prime of g of x. Like I said, you don't need to memorize things. You could derive them yourself, but it makes your life a little bit easier if you do memorize them or if you know the rules off the top of your head, so you don't have to go through this process of trying to find it. Because you are, like I said, you're going to be asked to find the derivative of an inverse function, and yeah, it's going to be a little bit tricky, but I think you guys will be able to do it as long as you know the rule. And if you don't know the rule, I'm just showing you guys can find it, right? You guys can find it. Okay, so let me see here. Let me write out an example problem I want you guys to try. Okay, so here, you guys try this problem real quick. Actually, you know what? Let's do this. I'm going to clear your pair deck. You guys can type in the answers on there. I'm going to put up 2 problems. I only want one of them done. But if you finish one early and you're still waiting, you should try the second one. Okay, you should try the second one. So try this first one. Okay, let's say I have a function f of x was equal to x squared plus 7. Okay, and the inverse function g of x, right? I'm sorry, g of x is defined to be the inverse of f of x. Okay, can you resend the pair deck? Of course. There you go. And back over here, right? And I tell you that f of, let's say, 5 is equal to 32. Okay? I want you guys to find g prime of 32 for me. Find g prime of 32. Can you tell me what that is? And if you're able to finish that and you're still waiting, I suggest you try this one over here. For number 2, I'm going to switch up the letters of the functions, and I'm hoping that doesn't mess you up too much. I hope you guys see that it's the same stuff, different names. So if instead of f of x, I'm going to call it h of x. H of x, right, is equal to x cubed plus x. And I'm going to tell you that h of 1 is equal to 2. I want you guys to find, also, let's see here. Let j of x be equal to h inverse of x. I want you to find j of 2, j prime of 2. Yeah, find the derivative of the inverse function evaluated at 2. So go ahead and start on that. Let me see where you guys are at on that one. So there you go on there. Double checking attendance. It looks like a couple more people have joined since I last checked it at the beginning of class. I'm still missing Cassandra and Juliet. So if you guys are here, could you type into the chat for me? If you're not here, I'm talking to no one. Oof, I'm sorry, guys. I hope this was okay of a lecture. I know this one's like a weird one, but honestly, once you get over my weird explanation of it, I hope you guys see that it's actually a little bit easier to deal with, right? As long as you know how to find the derivative of the inverse function. Whose name? Again, I'm missing Cassandra and Juliet. Juliet Vargas. Juliet Vargas. But yeah, I got you here, Jackie. I see you marked down on here. You got the little green check mark on my screen. I wish I could show you guys this thing, but I can't take this off this tab. But yeah. Let's see here. Yeah, I got the check marks for you. Yeah, the only people I'm missing is Cassandra. If you're here, Cassandra, let me know. And Juliet Vargas. If you're here, let me know. Hopefully you guys are doing all right. I know this was a tough one. Actually, it wasn't that tough, was it? I don't think it was that tough. I think it was okay. It was just weird. I'm thinking that stuff too much because I think it was one of those things that I didn't learn when I was learning calculus, and I should have. I did things the hard way because I didn't want to put in the effort to memorize these things. Instead, I was just like, I know how to find the inverse of a function. I can go ahead and take the derivative of that. And then I came across a cubic. And I was like, crap, I don't know how to find the inverse of a cubic if there's other x's in there. You guys can keep working this out, but I'm just letting you know. I remember some of the problems from my test, from the AP exam from like 20 years ago. And one of the problems was to find, if they told us that y was equal to like, it was like x cubed, right, plus some stuff. And they wanted me to find the inverse and the derivative of that inverse evaluated at something. Now, if it was just y is equal to x cubed, the inverse function is super easy, right? The inverse function of x cubed is just the cube root of x. And the cube root of x is easy to take the derivative of. You just power rule that thing. That would be 1/3 x to the negative 2/3. And then you just plug in the number, and then you get some number plugged in there, and then you'd be able to find the derivative of the inverse. Super easy. But I remember it was x cubed plus 2x. And because of that plus 2x, you can't just cube root the whole thing because then you'll still have an x there, right? It won't be undoing it. And I was just like, well, crap. How do you find the inverse of that? And it turns out you didn't need to. And my brain was stuck on the algebra 1 level of this class. And I was trying to do this calculus problem using like a not high enough level of algebra to do it. Instead, if I had just learned the calculus part, the calculus shortcut of it, I wouldn't need to do the algebra stuff. And that's the part that is like, I find interesting in this whole thing. Everyone always like thinks like calculus is a super hard thing. But the more you start going into it, calculus is actually easy. What's actually difficult in this class is the algebra work that you need to do. Anyways, I'm just ranting. It has nothing to do with you guys. I'm just complaining at the fact that, like, I don't know. Everyone always looks at calculus as like, man, this is like the god tier level of math. But when you go off to college, you're going to realize calculus is a freshman level course. It's the thing you take your freshman year. And it's actually pretty easy compared to all the other math that you've learned. Right? I know some of you are like, oh, what are you talking about? Quadratic formula, super easy, right? Solving quadratic, super easy. Solving trig functions, a little bit easier. They're actually not. They just give you the easier problems. The harder versions of those things are terrible, terrible. But the calculus part, easiest thing you'll deal with, calculus part. Calculus is easy. No one believes me though until afterwards. You gotta hear me out. Calculus is easy. It's the algebra that's hard. All right, let's see where you guys are at on this one. Let's see where you guys are at. That's that. Let me go over her. Calvin, you have this written out beautifully. Now let's start working on it. Brian, N, looking good. Already a great start. Already a great start. Keep going. Keep going. Oscar. Oh, be careful. Okay, so you got an answer for number 1. That's number 2. Be careful. That's not a G prime. That's a J. What the? Let me hide that. Yeah, for number 2, that's a J. So just make sure that you switch that with a J instead of a G. Ratish, you got the same answer for number 1 as other people. Number 2, yours is a little bit different. I don't know what the answer is yet, but I think you're close. I think you're close. I think you're close. Jeffrey, looking good on the second one. The first one, you got a different answer from other people, but I think it's close to what other people got. Jocelyn, nice smiley face. That 2x is the derivative of f of x, right? It's not the inverse function. Just keep that in mind. The 2x that you got there. Kaylee, looking good. I think those are the right answers. At least that's what other people have gotten so far. So it looks pretty good. Monica, same as what I said for Kaylee. Again, I don't know the answer, but you showed the work, so that looks good. Looks good for showing the work. And Fatima, you got the right idea. You do need to find the derivative of f of x, but be careful what gets plugged into what, right? G of 32 is a number that you need to calculate before we plug into the derivative. So G of 32, what the heck is G of 32? We got to find that. All right. Grace, is it Grace or Gracie? I should have been asking this like a long time ago. I'm gonna go with Grace. Either is good. All right. So Grace, that looks good. That looks good. G of 32 is equal to 5, right? Because f of 5 is equal to 32. G of 32 would go backwards on that one. All right, so it looks good, Grace. Joe, I think you're working it out, right? You got your number 1 and number 2 there. It looks like you had something there, but it's not there anymore. Leslie, looking good. I think that's what the answer that a lot of the other students have gotten. Again, I don't know the answer, but thank you for writing it down. It looks right. Compared to everyone else. Max, same thing for you for number 1. That's what a lot of students have gotten. Brian V, that's what a lot of students have gotten for 1 and 2. And Emily's working it out. Yeah, that looks good. Emily, keep going. That work is looking good. And there's 12 others who did not respond. I'm assuming you're working it out on something else. Diana, David, Eric, Brandon, Francisco, Cheyenne, Shirley, Julia, Angela, Sam, Kimberly, and Alejandra, right? Hopefully you guys are working it out on paper. But yeah, we're going to go ahead and I'm going to get started on explaining this one, right? So if I'm asked to find g prime of 32, I need to know that the derivative of the inverse function is going to be equal to 1 over the derivative of the original function of the inverse evaluated at the point that I care about, right? So looking at that and plugging this into here, I know that g prime of 32 is going to be equal to 1 over f prime of g of 32. So here's the 2 things I need. I need to find out what f prime is, and I need to find out what g of 32 is. So it doesn't matter which order you go in, but probably the g of 32 should be done first, because then that gets plugged into the derivative of f prime. I'm sorry, of f itself, right? So off on the side somewhere, I need to find out what the heck is g of 32? Well, if f of 5 is equal to 32 and g is the inverse function, g should take 32 and spit out 5. So that's what I know right here, that g of 32 is going to equal to 5. Second thing, the derivative evaluated, right, of x, I'm sorry, derivative of f of x is going to equal to 2x, right, which means I'm looking for the derivative evaluated at g of 32, but I know that g of 32 is just equal to 5. So I didn't have to write g of 32. I could have just wrote 5 in there. And that's going to tell me that f prime of 5 is going to be 2 times 5, which is just equal to 10. So with all that work being done, the derivative of the inverse, right, of f of x, or derivative of g, I should say, is going to be equal to 1 over 10. And you're done. Ta-da! I know, it's like, what, that's it? That's all you got to do? And yeah, that's it. That's pretty much the idea. You just need to find out what the inverse function, what it originally started off with, right? If the inverse function is trying to look for it for 32, what the heck was the number that got you that 32 in the original function to begin with? And you can actually see that if you plug this in. 5 squared plus 7 is actually equal to that 32. That's where this idea comes from. It comes from the fact that if you plugged in 5 into x, you'd get 32. So if you plugged in 32 into the inverse function, you get back 5 because it's the inverse. All right, let's wrap this up here. For this one, for number 2, it's almost, actually, I should say, it's the same thing, right? It's just not using g's and f's. It's using j's and h, right? So the derivative of j evaluated at 2, since j is defined as the inverse function, I can use the rule for the derivative of the inverse, meaning the derivative of j is equal to 1 over the derivative of h of j of 2. I hope you guys are okay with that. It doesn't actually change the problem if I switch the g's and the f's and use it as j's and h's instead, okay? And that's going to be finding, well, then I need to find out what j of 2 is. Well, what's j of 2? Hope you guys can see that. If h of 1 spits out 2, j of 2 spits out 1. The derivative of h, well, what's the derivative of x cubed? X cubed is 3x squared. What's the derivative of x? I think I saw now what some of you guys might have forgotten about. You might have forgotten that 1. The derivative of x is not 0. The derivative of x is 1, right? The derivative of x is 1. So h prime of j of 2, right, is just a fancy way of saying what is h prime of 1 equal to? And that's going to equal to 3 times 1 squared plus 1, which is going to equal to 4. So my answer for this, j prime of 2 is going to equal to 1 over 4. And that's it right there. That's my answer for number 2. Okay? That's my answer for number 2. Is that all right, guys? Does that make sense? Does that feel pretty good? Hopefully it does. Derivative of inverses, like I said, it's not something that you should be overthinking as much as I've been talking for so long about this problem. But it's just something that I wanted to show you that it's supposed to be there to make your life easier. If you're ever asked to find the derivative of an inverse function, you don't need to find the inverse function and then take the derivative of it. You can just use this shortcut. But yeah, one other side note before I let you go. Sometimes they don't use different letters like J and H's and G and F's, right? If we're given G prime without the X value, we just plug it into the calculator like you showed us earlier. Yeah, to try to find out what it is, but you plug it into the original function f of x that you're dealing with, Monica. But before we do that, we'll do some more practice. I won't give you a problem without giving you the point just yet. Even that, I don't think they do that on the AP exam unless it's on the calculator portion. But most of the times they give you a point, Monica, so you can make the relationship between f of x and its inverse. Okay? So yeah, just keep that in mind. Just a side note, by the way, some problems don't define the inverse function with a different letter. They just define the inverse function with the inverse notation. And it gets really confusing. They sometimes write things like this. They'll say, let f of x be equal to a differentiable function, right? Right? And then they'll say f inverse of x, and they'll write it like this. And they'll say the derivative of that. So this is horribly messy, horribly ugly, but they do have notation that looks like this, by the way. And when they do it like this, it's still the same thing. It's still going to be equal to 1 over the function's derivative of f of the inverse of that. And I don't want you to be confused by this right here. It's the same thing. It's just that instead of writing out that g of x is equal to the inverse of f of x, they just skip this whole part of using g and they just use this notation instead. And it's the same thing. You still look for what the inverse is at a specific point and plug it into the derivative of that. Okay? All right. I believe I posted some homework problems already for this for you guys to try. It starts at like number 9, so don't be thrown off, or it starts at like number 7 or something like that. So don't be thrown off when you see that. And there's going to be one problem with the table on there, and we haven't gone over how to calculate it with the table yet. So, just hang off onto that until I go over it, or you can try it on your own. All right, guys. And that's it for me today, guys. It is 10:37. And yeah, I'm going to see you one more time tomorrow before we go on Thanksgiving break, okay? So have a good rest of your day, guys. I'll see you tomorrow for 30 minutes, and then we're going to go on Thanksgiving break, man. All right. See you guys later. Have a good one. I have office hours today. I will not have office hours tomorrow. You do have math tomorrow, Calvin. Tomorrow is all periods for 30 minutes. All right, guys. See you guys later. Bye, everybody. Bye-bye. So long.